Welcome to the lesson video for regression trees. In this video, we're going to talk about regression trees, which are an easy to understand method for regression and, as we will see later, for classification. So what is a regression tree? A regression tree is simply a set of thresholds or decisions that we're going to make, and we follow each of these decisions, and then we get to the end, we are provided with the number, which is the estimate for our observation. And so it's easiest to understand from a diagram like this. And so let's walk through an example. It's easier to walk through an example than try to define a regression tree abstractly. So what we do is we start with this inequality that's provided here, years number 4.2, and we're trying to predict a player's salary in the hitters data set. So this is the data set we're provided with a number of statistics about a baseball player and we'll predict his salary. So we look at whether his years are less than 4.4. So if he's been in baseball less than 4.5 years, then we follow this left-hand branch, right? And so left hand always goes with yes, and we find that his predicted value, his predicted salary, well, the predictions are given in log, so it's log of the salary is 5.11, or his predicted salary is 165,000. If he has been in baseball more than 4.5, we follow the no branch, and then we come down here and we look at his hits. If his hits are less than 117.5, so that's the number of hits that he's gotten in the previous season. If the hits are less than that, then we follow this branch, and we would predict his salary to be 402,000. If his hits are not less than that, we would follow the right-hand branch, and we predict the player's salary to be 845,000. So why would we do prediction this way? Well, trees work well with qualitative predictors. That's one advantage. We've checked a threshold on years and hits in both of these cases, but if it was some sort of qualitative predictor, then you could send one category down one side, another category down the other side, and it would work fine. A lot of our regression methods, linear regression, they don't work well or easily with qualitative predictive variables. You have to do some work with those to get them to work. These models, and this is really one of the main reasons we care about them, they are the building blocks for some of the top performing regression and classification models. So regression trees are used an enormous amount, particularly in certain types of classification regression problems, as building blocks for more complicated models. If you look at what we've done here, you might estimate, and you'd probably be correct to say, this doesn't seem like the most accurate way to predict a baseball player's salary, and you'd be correct. Regression trees have some level of predictive accuracy, but alone they're not the best. We use them as building blocks for more complicated things. But one of the main benefits of regression trees is that they are human interpretable. So you and I just walked through this regression tree and followed this very simple model, and I didn't have to define anything for you, and I hope it made sense because it's pretty simple. Doctors, personnel in a hospital will use these sorts of regression trees or charts that basically give the same thing. They'll look at a blood pressure. If it's bigger than this or less than this, they go on down to the next criteria. And at the end, they get to some diagnosis. And doctors really like this because it's easy to follow the tree, and yet the doctor can apply their own intelligence and say, I have some specialized knowledge. I understand what the tree is telling me, but I can either say it's correct or incorrect, but I understand why it's doing what it is. So it's not just that it's going to be quick and easy to use, but also the person can tell why it's making the decision, and the doctor, with the specialized knowledge, may know why it's going to be overridden. So for example, if somebody's temperature is off, the doctor could say, well, I know this person just ran down the hall or something that would make their temperature off, or blood pressure or whatever. Okay, so let's talk a little more detail. So this is the regression tree we're looking at on the previous slide. A little bit of terminology. We've used the term branches. So when you start at one of these decision points and then you have two options, left or right, those are called branches. These points where we're making decision, they're called nodes or splits. And this tree terminology, branches or nodes and splits, kind of follows down through a lot of the work with decision trees, regression trees, and classification trees. These terminal nodes, these places where you end, they're called terminal nodes, or leaves. Leave being the thing that occurs at the end of a branch. Now, we can look at this left-hand side that we have the regression tree. On the right-hand side, we have a plot of our data set, a scatter plot, years on the horizontal axis, hits on the vertical axis. So if we look at data points that come in and we look at this regression tree with years less than 4.5 and we follow this left-hand branch, then we arrive at this leaf or this terminal node 165,000. So let's look at this decision, years less than 4.5. So right here on the years axis is 4.5. So everything with years less than 4.5 is this region that's labeled R1. So R1 would correspond to that node. So everything in this region R1, we predict that salaries for those baseball players to be 165,000. If we follow the right-hand branch and go down to the hits, so the right-hand branch is everything that's going to be with a years greater than 4.5. So it's this box. Everything inside there would go down the right-hand branch, then hits less than 117.5. That would be checked. If it hits is less than 117.5, we'd go here. And so less than 117.5, right there's 117.5 on the hits axis. And I don't know, maybe we'll attempt to say we've gone down this side. Hits are less than 117.5, so we're going to predict 402 salary for everybody in region 2. And then way too much color. Let's grab green. So everybody whose hits are not less than 117.5, so they're just all these players have more than 117.5. Those are the players up here in region 3. And everybody in region 3 winds up, and the prediction for anybody in region 3 is that their salary is $845,000 per year. So it's rather crude. If we continue and we make more branches in our tree, we split additional times, we'd find smaller and smaller rectangles, and we divide up the space further. Okay, and as we've talked about for each box, so for region 3, how did we estimate this as 845,000? We took the average of every point in that box. The average salary for all the people in that box was 845,000, so we apply that as the predicted value for anybody winding up in that box. Okay, so when we're building a regression tree, we usually call it growing the tree, following the regression tree terminology. We grow the tree one node at a time, moving down. So the first step is to decide on the variable and threshold for the first split. So then we create our first split, which in this case is years less than 4.5. And we follow the left-hand side, and it doesn't matter whether we follow left or right first, but for convention here, we follow the left-hand side first, and we decide, okay, we're going to make that a terminal node. Everybody there will assign their salary to be 5.11 to be the log of their salary. And then we figure out what goes on in the other branch. We get down there and we say, okay, we don't want to make that a terminal node. We want an extra split there. And then we have to decide to make those terminal nodes at each of the branches from that split. So we really have two decisions we have to be able to make. We have to be able to make a decision of whether we are at a terminal node or not. And we have to make a decision of what variable we're going to use and what threshold we're going to use to make our decision at the node. So let's talk about how we do that. How do we choose the variable and the threshold for each split? So in this diagram, we started with years less than 4.5. How did we make that decision? And when we got down here, how did we decide that we should use hits less than 117.5? So here's what we do. At each node, you look at each predictor variable, and you check every possible threshold, and you choose the predictor variable and the threshold. So predictor variable xj, threshold, which we call s, and the threshold is also called a cut point that minimizes this squared error. So the way this formula works, this is the predicted value for region 1, right, going down the left-hand branch, say, and this is the actual value for y. So this is the sum over all data points that are going to wind up in region 1, and then we look at the squared error for those, and then this is region 2. Here's the sum over all data points that wind up in region 2, which would be the other branch, right? One side of this equation is left branch, and the other side is right branch. It doesn't really matter which we call left and right, of course. And we sum up the squared error for everybody that winds up in the right-hand branch. This is the predicted error for everybody in the right-hand branch, and or predicted value for y, and this is the actual value for y for each of those data points. This takes a little bit of searching, right? You have to search through all your predictor variables, and if you have 100 data points, you might have 100 values for those predictor variables, so you would check each predictor variable in every possible threshold, right? Threshold between every pair of values that you have for data points in that variable. So that'll find us the variable and threshold that will give us the minimum squared error if we just made the prediction at this point going down those two branches. How do we decide to make a terminal node? Right down here, we decided everybody down there, we're just going to call them 165,000 as their salary. Well, the most common way to determine that you're at a terminal node is just stop node contains the minimum number of points. So this tree here could have been constructed saying, hey, we're going to stop when we hit a node that contains 100 players or 50 players. I'm not sure how many are in those terminal nodes, but there's some number, and they say when we hit a certain number of players, we're not going to divide this any further. If the minimum number of players was 10, we would have grown this tree out further. And this is a really important thing. If you grow the tree down, say you said your minimal number of points was 1, like to take an extreme example. Let's go back up a slide, 2 slides. Look at this. Well, now it's all covered all over with ink on the right-hand side. But if you imagine what would happen if we picked 1 as the stopping point, you would have a rectangle around every single point. And then everybody's predicted value would just be the value of that data point. And I'm going to be here all day if I try to draw it in that point. So that would be way over training. That would be, you're looking at something that winds up being similar to k-nearest neighbors at that point with using just one nearest neighbor. Okay, so what we usually do, and this is really important, is that we grow the tree more than we need to, and then we scale it back, which, following the tree terminology, is called pruning, so that we're scaling back some of the terminal nodes, and that creates a final tree. So we grow it further than we need to, and that tree would be overfitting, and then we prune it to scale it back. And we prune it far back enough, we decide how far we're going to prune it using a cross-validation approach. So a little bit more information about pruning. If you think about, we're just going to scale it back and we're going to use cross-validation to pick the best scaled back tree, that would not be a bad way to think about pruning. Here's a little more detail about how that's done. And so we start with this statement here. So for each value of alpha, and alpha is going to be kind of a tuning parameter for our pruning, there is a tree T, which is a subset of our main tree. So this T naught is the tree that we get to when we grow fully. And T is a subtree, meaning it's created by getting rid of some of the terminal nodes in T naught, repeatedly scaling it back, such that this formula here is as small as possible. And so what's this formula? The left-hand side is simply the sum of squares error for the tree, right? So this is difference between the actual value and the predicted value squared, and then we sum that, so it gives us sum of squared errors. This absolute value bar is T, that's the number of terminal nodes in T. So we have this piece here, which is your error, right? That's residual sum of squares error for the tree, or over every rectangle in our variable space. And then that piece on the right-hand side, that's alpha times the magnitude of T. This is alpha times the number of terminal nodes in the tree. This is a penalty term on the complexity of the tree. So the larger you picked alpha, the more this penalty term will matter, and the more scaled back or the more pruned your tree would be. And so for each alpha, there is one tree that makes this as small as possible. Alpha is going to control how much weight is put on the tree size, and then we pick alpha. We're going to pick alpha using cross-validation. So you think of this alpha parameter, 0 is the smallest it could be. If alpha is 0, we're looking at the full tree, and as alpha increases, the tree is going to have fewer and fewer nodes. So here's a way to think about it. When alpha is 0, you have your full tree. This is the full tree for the predictive hitters tree that we were just looking at. As you increase alpha, and maybe there's an alpha value that's here, and we've pruned back a little bit, and then there's an alpha, pick an alpha value further out, and we've pruned back, And then there's our most approved tree. And then we would use cross-validation to pick what alpha value we should use. This should be a similar scheme, similar to ridge regression, lasso, a number of things we've seen where you have a penalty on the size, and that size, if it's too large, it gives you too much variance and you wind up with variance error. So we use cross-validation to pick that parameter. Okay, so review what we've talked about today. We talked about regression trees, and here is a picture up in the top right-hand side. If you want to remember how regression trees work, I like to have a little picture that helps me remember things. It's a pretty good picture to remember. So on the left-hand side, there's just a sample set of data. On the right-hand side, there's the function y is a function of x1 and x2 that would result from that regression tree. So we talked about regression trees. We build the trees sequentially, choosing each split that minimizes the residual sum of squares error. Then we're going to prune back the tree to reduce overtraining. Why do we do this? Why do we want to use regression trees? Well, trees work well with qualitative predictors, and that's a pretty big deal, as we'll see when we get into using them. A lot of the methods that we've talked about, there are a lot of methods that are good, but only work well on continuous variables, continuous predictor variables. Trees work well with qualitative predictor variables. These trees model are the building blocks for some of the top performing regression and classification methods, and these trees are easily human interpretable, as we've talked about. Thank you very much for watching.